All right, welcome back everyone. So in this video, we're going to look at a second example of an inverse Laplace transform, except this time the inverse Laplace transform is going to require a little more work, and that's going to be with partial fraction decomposition. Okay, so this is a main reason why you learn this in Calculus 2 is that we utilize this a lot when we do Laplace transforms, inverse Laplace transforms. So that Calc 2 integration technique, partial fraction decomposition, comes back into play in this situation, is utilized a lot. Okay, we're going to try to inverse Laplace the following function, s squared plus 6s plus 9 over s minus 1 times s minus 2 times s plus 4. Okay, so here we have to use, you know, partial fraction decomposition. Okay, so when you do these problems, it's always good to have a table near you to help you out in case you need to recognize some Laplace transforms, revert them back into functions of t in case, you don't know them off the top of your head. So let's go ahead and get started on this problem. So we want to start partial fraction decomposition on this function. So, the way we would do that is, we would say like partial fraction decomposition. And so we have s squared plus 6s plus 9 all over s minus 1 times s minus 2 times s plus 4. And we need to term by term decompose this. So we would say is a over s minus 1 plus b over s minus 2 plus c over s plus 4. Okay, and what we are essentially doing is turning this into the inverse Laplace of, a over s minus 1 plus b over s minus 2 plus c over s plus 4. So that's what we're turning this big term, rational term into so that we can inverse Laplace it because we cannot inverse Laplace it right now as it is. So let's figure out what A, B, and C are so that we can finish up this problem. So in order to find A, B, and C, we need to multiply both sides by the least common denominator, which is the denominator that we originate with, s minus 1, s minus 2, s plus 4. So hopefully you recall this from Calculus 2. Okay, so when we do that, this whole term goes away. On the left-hand side, the denominators all go away on the right-hand side, and what we are left with is s squared plus 6s plus 9 equals a times s minus 2 times s plus 4 plus b times s minus 1 times s plus 4 plus c times s minus 1 times s minus 2. Okay, so what we want to do now is figure out what A, B, and C can equal. So when you learn this in Calculus 2, hopefully you learned about two different methods to solve this, one being a system of equations or one being choosing values to eliminate other values. And I prefer the elimination type of method. So we're going to do that right now because a system would be about like three equations, three variables, and that gets a bit tedious with your algebra. So what we're going to do is my preferred method is pick S values that make solving A, B, and C simple. Okay, so I want to figure out what A is. Okay, so the best way to figure out what A is to eliminate B and C and just get A equals something. So what do B and C have in common that could give me 0 there? Well, they have S minus 1 in common. So if I set S equal to 1, I would get 1 minus 1 times B and C, and those just go to 0. So what I'm going to do is let S equal 1 to get A. So I'm going to plug in 1 for every single S, so it'll be 1 squared plus 6 times 1 plus 9 equals A times 1 minus 2, 1 plus 4 plus B, 1 minus 1, 1 plus 4 plus C times 1 minus 1 and 1 minus 2. Okay, well, 1 minus 1 is 0. 1 minus 1 is 0. So anything times 0 just goes to 0. And so what I'm left with on the left-hand side is, you know, 1 squared plus 6 plus 9 is 16. And then A times -1 times 5 is -5A. We could say plus 0 if you want, but, it's unnecessary. And so divide -5 to both sides, I get 16 over -5. All right, so that is A. And we're going to do the same process to get B and C. So let's look at our setup here. So I already know what A is. I don't need to worry about what A is. Uh, but how do I get B and C? So let's focus on B first, right? What do A and C have in common? Well, they have a common term S minus 2. So if I plug in 2, A and C are going to 0. They're going away, and I can just focus on B. So what we're going to do is let S equal 2. We're going to let S equal 2 to get B. So let's plug that in, right? Plug it into the function 2 squared plus 6 times 2 plus 9 equals A times 2 minus 2, 2 plus 4 plus B, 2 minus 1, 2 plus 4 plus C times 2 minus 1 and 2 minus 2. So A and C both go to 0. Anything times 0 is 0. And so what I'm left with, 2 squared, that's 4. 4 plus 6 times 2 is 12. So 16, 25. All right. And so what I'm left with is 6B. And so B is just 25 divided by 6. All right, great. And last thing to do is get C. What common term do A and B have? They have S plus 4 in common. So what we're going to do is make S -4 to get those going to 0. So let's go ahead and set S equal to -4. All right, so let S equal -4, and this is to get C. So -4 squared plus 6 times -4 plus 9 equals A. -4 minus 2 times -4 plus 4 plus B, -4 minus 1, -4 plus 4 plus C, -4 minus 1, and then -4 minus 2. Okay, so A and B both go to 0. And what I'm left with is -4 minus 1 is -5 times -6, which would be 30, positive 30. So positive 30c equals 16 plus -24 plus 9. That ends up being just 1. So C is 1 over 30. All right, so we figured out what A, B, and C are. Okay, so we figured out what A, B, and C are to our partial fraction decomposition. So we did a lot of this side work. Let's bring it back to the Laplace. All right, so here I'll say, now come back to Laplace. And so the inverse Laplace transform of s squared plus 6s plus 9 over, s minus 1, s minus 2, s plus 4. Well, that equals the inverse Laplace transform of A over s minus 1, which is negative 16 over 5 over s minus 1, plus B over s minus 2, which is 25 over 6 over s minus 2, plus C over s plus 4, which is 1 over 30 over s plus 4. And, if you want to take it a little step further, just to make sure you're understanding what's going on, it's like A over s minus 1 plus B over s minus 2 plus C over s plus 4. And we just plug in A, B, and C. So almost there. We just got to figure out how to inverse Laplace these terms. And we did most of the hard work, but one thing we could do is separate these inverse Laplaces. So, we could do negative 16 over 5 over s minus 1 plus the inverse Laplace of 25 over 6 over s minus 2 plus the inverse Laplace of 1 over 30 over s plus 4. All right, and we're still trying to inverse Laplace these, so one thing that might help is to take the constants out. So, maybe I'll make another note here like separate and then, take constants out. So what I'm left with is inverse Laplace, sorry, taking the constant out, 16 over 5 times the inverse Laplace of 1 over s minus 1 plus 25 over 6 times the inverse Laplace of 1 over s minus 2 plus 1 over 30 times the inverse Laplace of 1 over s plus 4. Okay, so this is where having a table handy to us would help us figure out what do these Laplace transforms look like originally. So let's go up to that table we have all the way up here. And so all of these are like 1 minus over s, minus something. And to me, this fits the exponential criteria. E to the AT is 1 over s minus that a. Okay, so to me, I'll say looks like e to the AT. And so here, a would be 1, a would be 2, a would be -4. Because what is the Laplace of e to the at? That's 1 over s minus a. So the inverse Laplace of these guys would be negative 16 over 5, just e to the t, because a is just 1, like 1t, but we don't need to write that. Plus 25 over 6, e to the 2t, plus 1 over 30, e to the negative 4t. And that is our answer. Okay, so yeah, quite a bit of work to get to this point. It was really like two problems in one where we had to use partial fraction decomposition and then inverse Laplace to get our final answer. But that's how an inverse Laplace of this type of rational function would be. But okay, thank you for watching. Thank you for sticking with it. I'll see you in the next video. Take care.